So in today's lesson, I want to talk about something that we're pretty familiar with, which is Young's double slit experiment. But I want to talk about it in reference to our conversation yesterday, which was about wave interference. So you'll remember yesterday that we looked at a two-source wave interference pattern, right? So if we had two little sources here, well, we know that there's going to be, this guy's going to create a wave and then a circular wave and this guy's circular wave. And then as these get larger on each side, we're going to see some interference happening at different points along the way. And you'll remember that we saw hyperbolic shaped sort of nodal lines as we went across, and so on and so forth, and those created sort of like these blank areas that we could see on the screen. So many scientists, the idea was that if this worked with water, okay, so when we did this was with water, which was super easy to see with the naked eye. Scientists thought, well, if we can do this with water, and we know light has wave properties, we should be able to see the same thing if light indeed does behave like a wave. So lots of scientists tried to perform this experiment, but they failed. They were not able to do this, mainly for a couple of reasons that are really related to each other. The first is that, light, the wavelengths of light are really, really, really small compared to, water waves, for instance, right? And so that made it difficult to get our light source to emit the light in phase. You'll remember that when we were looking at our two-point interference, these 2 point sources here were in phase with one another, right? So like essentially it was like, if you're touching water with the tips of your 2 index fingers, they were hitting the water at the same time in phase. So this is difficult to do with light because of its small wavelengths and so hard to kind of see. So famous guy, Thomas Young, he did this famous experiment, and we've seen a video about this already. He tried to figure out how to solve this problem, and what he did was instead he created these barriers, so with 2 little slits here, and he had one light source. So for instance, he might have had like a bigger slit sort of right here, and then he would have light waves coming through this one source. But then when they would hit this barrier over here, then they would travel through they would diffract through these 2 point sources so that they would be completely in phase with one another. So the light diffracted through those tiny, tiny little pinholes, and they had to be small because the wavelength of light is so small. And so because the spacing was close together, these slits, they were able to see nodal lines large enough that were able to be observed, which was pretty cool. So you'll remember from some of our other conversations, and videos that we've watched together, that what you end up with are a series of these really bright bands right here that form on the screen, where these light waves are kind of passing through and hitting a screen past those 2 little open slits. But there are also these sort of darker bands in between. And so I'm going to talk a little bit about that. So here we see, the first screen and then the second screen that allowed, the first screen is our original light source, and then the second screen with those 2 slits allowed for the wavelengths of the light to pass through in phase. So Young called these interference fringes, okay? That's what he called these little dark and light bands. Specifically, he called the light bands maxima. Okay, those were areas of maximum constructive interference, and the dark bands were areas of they're called minima, and those are areas of maximum destructive interference. There's another picture that I have here that I think will be helpful for you to make sense of this. Just let me pull it up. Let me see, here we go. Right, so if I were to kind of zoom in, so here's our original light source right here, and then here are our two slit openings. Well, we're going to have light, let's say I have this, here's this first light wavelength coming through from the one source, and then here from the other one. We see that at this point here, really they're just meeting completely in the middle. And where they're meeting constructively, that's in this circle right here, the zoom in, then we see a bright band. That's our bright band. But if we see that they are out of phase with each other, right? So there's one has to travel a little bit further than the other to get there. Remember the path length difference that we spoke about yesterday, right? So this line right here has to go a little bit further. So they're not completely hitting they're not equal distances, and so that will mean that they will reach the screen out of phase. In other words, they will interfere destructively, and so we will see that as a dark fringe, and so on and so forth. So let's examine that a little bit more closely. That bit about constructive and destructive interference. So, when I say that theta is at 0, I'm talking about, the angle from that perpendicular bisector. So theta is 0, I'm talking about the fact that right here, there is 0 deviation from that perpendicular bisector. If we see that, then we know that the waves are going to reach the screen in phase at that center point there, and that's going to create that constructive interference, and we're going to see a nice light band at that point, a nice maxima. Okay, if they have to travel an extra half a wavelength to reach the screen, then we see that their path lengths are different, right? So if their path lengths are slightly different, then they're going to interfere in a destructive manner, and that's going to give us that dark minima that we saw, and so on and so forth. And of course, once our path length is an even number again, is lambda again, then we're going to see that those waves are going to be back in phase, and it's going to produce another bright fringe, and so on and so forth as the pattern goes. So the first equation that we saw yesterday, allowed us to make some calculations relative to those nice nodal lines. And so let's take a look at that again, because it's going to apply here. So whenever we see the destructive interference, in other words, we see those minima or the dark fringes, so dark, we're going to use this formula right here. And so sine theta is equal to n minus 1/2 lambda over d. So the variables representing, our theta is the angle formed between the nodal lines. N is our nodal line. D is the distance between our point sources, and lambda is of course, our wavelength. Constructive interference we're going to look at as, those are our bright fringes. Those are our bright fringes, our maxima. And we're going to use this formula too. I should let you know that in some textbooks you will see sine theta m equals m lambda over d. And again, we're looking at the bright fringes in the nodal lines there. So I just want to review yesterday's formula, the formula that we looked at yesterday, this guy right here, and remind you of some of the finer details related to that. So remember, we're talking about 2 point sources, and of course, as light is behaving like any other wave, what we saw with water waves is also going to apply here today. So if I have, my 2 point sources, S1 and S2 here, here we go, boom and boom. Those would be this, like our slits, right? And I'm just going to simplify it by putting little dots as our point sources, but really those are slits with Young's double slit experiment. I'm going to talk about some point sort of way over here that's on a nodal line. I'm going to call it PN, and N being the nodal line that that point would be found on. If I go ahead and I join my point sources, in other words, the slits to that, I can also look at the midpoint between those 2 point sources, my perpendicular bisector here. Well, L would be the distance from my point source to that point on the line. And no, sorry, drew that wrong. L is the distance from my midpoint all the way out to that point on the line. There's my L there, okay? And X is my horizontal distance to that nodal line. So that's this guy right there, okay? So in my formula, theta ends up being this guy right in here. Here's my theta. Okay, xn is the horizontal distance from my perpendicular bisector, and L is that distance from the midpoint of the 2 point sources to the point on my nodal line. And what is D? Oh, that's the only part I haven't talked about. D is, of course, you'll remember the distance between my point sources, like that. So for each nodal line that I see, you know, I can isolate X here. So all I've really done is I've just taken this part of the formula, and I've taken L, and I've isolated my X, which is, you know, really just my horizontal distance from the perpendicular bisector out to that point. So extending this further, oopsies, extending this a little bit further, I come up with an equation that allows me to derive an equation describing the distance between all of the nodal lines. So in other words, a delta X value. So what am I describing when I'm describing the delta X value? Well, let me see if I can draw a nice little picture of this. So if I have my slit number 1 over here, and I have my slit number 2 over here, right? And in between them, I have my midpoint. So I'm going to draw that little midpoint here. And I'm going to have a bunch of different nodal lines. Okay, oops, I should probably, you know what I'm going to do? I'm going to draw my right bisector here, and then I'm going to draw those nodal lines in a different, so I might have, you know, my nodal line number 1, so n equals 1. I'm going to have each of those, one of those on each side. And, you know, and another one here, n equals 2. N equals 2. Right, and all along in here I have my theta, so here's theta 1, theta 2, or theta 1 again, so it's the same angle, theta 2, right? And so, you know, each of these is going to represent a dark and a light band. So actually, you know, this distance here, okay, remember that light band, right, would go from here to here. That would be a light band. And so that is what my first delta X. Okay, but then I would have another dark band right in here, right? My next minima right in here. And then same on the other side, there's my dark fringe on this other side here, right? And so I have, you know, light band, dark band, and so on and so forth. So what this formula here that I have on the right allows us to do is to determine what that distance between the nodal lines is. So let me write some of this out here. So this x right here is the distance between nodal lines. Okay. Lambda is, of course, the wavelength. L, in this case, describes the perpendicular distance from slit to screen. And D represents, let me do that in a different color. D represents the distance between the slits. So it's important to distinguish this little bit here about the perpendicular distance from the slit to the screen, because it's not the same L as we saw in our last video. And so if I'm looking at that, really all that L is my distance from wherever this screen is here. Wherever my slits are, all the way to where the screen is. So this is what L is in this case. It's really just the distance from the light source to the screen. And so that should actually make things a little bit easier for us. I think we're ready to take a look at some problems. So maybe take a minute to have the equations that we are going to need for this, for these examples kind of ready and put aside so that you can have them, have easy access to them. So let's take a look at this example together. It says, you're measuring the wavelength of light from a certain light source. You direct the light through two slits. Okay, so there we go. That's telling us where to look for our formulas, with a separation of 0.15 millimeters, and an interference pattern is created on a screen 3 meters away. You find the distance between the first and 8th consecutive dark lines to be 8 centimeters. At what length is your source radiating? Okay, so we should probably start by writing out some of our givens. So let's look at this. So the first thing I'm seeing here is that the slits have a separation of 0.15 meters. So I'm going to go ahead and write that, well, what is the variable used for the slit distance? That's D. So D is 0.15 millimeters, and of course we want to get that into meters. So converting that to meters, 1.5 times 10 to the power of -4 meters, right? It's going to be a really small distance between those sources. Okay, next. So the next thing I have is that an interference is created on a screen that is 3 meters away. So that's telling me that the distance between my screen and my light source is 3 meters, so that is L in this formula. So L is equal to 3.0 meters. All right, the next part is a little bit trickier, so it might help for me to draw a bit of a visual for you. All right, so it says that the distance between the first and 8th consecutive dark lines is 8 centimeters. Okay, so I'm going to draw that out. Here we go. So let's say this is our first dark fringe. So, oopsies. We're going to say this is our first dark fringe, right? So in other words, this is n equals 1. And then, 2, 3, 4, 5, 6, 7, 8. And so here's n equals 8. But how many delta x's do I have in here, right? I have 1 delta x, 2 delta x's, 3 delta x's, and so on and so forth. 5, 6, 7. So in order to get my overall delta x value, I'm going to say, well, I have 8 centimeters divided by 7 of those little differences, right? And so that's going to give me, you know, the value for a single delta x, which is 1.14 times 10 to the negative 2 meters. That's what that works out to be. All right, and so what am I looking to solve here? I'm looking to solve for lambda. I want to know, well, what is lambda? So I'm going to employ the formula, well, delta x over L is equal to lambda over D. Substituting and solving for lambda, lambda is going to be equal to my 1.14 times 10 to the negative 2. Oops, I'm running out of room here. Times my distance, which is the 1.5 times 10 to the negative 4 meters. Oopsies. And I'm going to divide that by my screen distance, right, which was the 3 meters. And when I work that out, my value for lambda is 5.7 times 10 to the negative 7 meters, which makes sense, right? If I'm looking at this in terms of nanometers, that seems about right. Okay, so let's try another question and see how we do. Hopefully you found that to be okay, except for maybe the little bit about these dark fringes and how to work that out, but hopefully our discussion will help to clarify that in future problems. Okay, so next question. Let's read it out together. Example number 2. The third order dark fringe of a 652 nanometer light is observed at an angle of 15 degrees when the light falls on 2 narrow slits. So again, we see the 2 narrow slits. We want to know how far apart are the slits. Okay, so let's break this down. Let's write out some givens. Well, what are some things that we know for sure? Well, they're telling us theta, and I'm going to just write out theta as 15 degrees here. Okay, it's telling me that it is a third order dark fringe, third order. So third order is telling me that my nodal line, I'm talking about the third nodal line. It's also telling me that the wavelength of light is 652 nanometers, so I'm going to write that out. And of course, I'm going to want to convert that into meters. So 6.52 times 10 to the power of negative 7 meters. And so what am I trying to find here? Well, I'm trying to find out how far apart the slits are. And so what am I really looking for? I'm looking for D, right? D is the variable that we use to represent how far apart, you know, the point sources are. Okay, so which formula to choose? Well, hopefully when you saw the fact that it was the third order dark fringe, you remembered that I need to choose the formula describing the wavelengths and variables relating to the dark fringe. So that is this guy right here. That is sine theta. And of course, if it's theta n, and it's our third order fringe, we're going to call it sine of theta 3, you know, is equal to n minus 1/2 times lambda over d. And so let's replace some of these variables. So sine of 15 degrees is equal to 3 minus 1/2. Okay, n is 3. Our lambda is 6.52 times 10 to the negative 7 meters. Oops. And I'm going to divide that by D. So isolating D in this formula, I get a value for D of 6.30 times 10 to the negative 6 meters. And that makes sense, right? Remember, we're talking about light, And in order to be able to see some really clear nodal lines, I'm going to want the distance between the point sources to be really close together. Okay, so hopefully you found that to be not too unmanageable, particularly given our conversation yesterday and what we've already talked about in class. Here are some suggested homework problems for you to try. Now, on our calendar, we're scheduled to have a Chapter 9 light quiz, which would include everything up into and including what we've done today. However, I'm going to postpone this quiz until Thursday just to make sure that we're all in the right spot and prepared to be able to write this quiz on Chapter 9. So if you have any questions, be sure to reserve them for tomorrow, at the beginning of tomorrow's class, and we can discuss.